To understand the photovoltaic cell, let us start with another PN junction, the well-known diode. Let us connect this diode in a circuit. A typical circuit for this would be something like this, where the diode is part of a much more complex external circuit as shown here. Let us put in some terminals. So this portion of the circuit, the diode along with these terminals is of interest, and let us study its characteristic before we try to understand the photovoltaic cell's characteristic. Let us call this terminal as A for anode, and let us call this terminal as K for cathode. And we know that the current always flows from the anode to the cathode in the case of the diode. We call this as the current I. Another parameter, terminal parameter of interest, is the voltage across the terminals A and K, and we call that VAK. So it is of our interest to study the diode PN junction in terms of the current through the diode and the voltage across its anode cathode terminal VAK. So with this polarity of voltage VAK being taken as positive, that is the non-arrow end as the common point for probing and the arrow end as the positive terminal for probing for the voltage, and the direction of the current as shown here as positive, then we say that the power flows into the device, and the device is acting as a sink, and the power flow is into these one-port terminals. The object of interest now is the diode part. So we'll bring the focus to the diode. And this diode, in its present representation as it is drawn in this circuit with the current flowing into the terminals, anode terminal, and with the voltage indicated as thus, and the power flowing into the diode terminals, the diode acts as a sink, which means it receives power and only dissipates. It cannot generate. So this particular portion of the diode circuit is now a sink circuit and not a generator circuit. We will gradually see how we make it into a generator circuit and what extra components we need to add in order to bring about the model of the photovoltaic cell. Let us now make some space for drawing the characteristic. We will reduce this portion and keep it there. Let us have the x-axis, and we shall mark it as VAK. This is the voltage axis. And then we have the y-axis. We shall mark it as I and draw the IV curve. The IV curve of this particular diode is very familiar to all of us. We will stick to drawing mainly the forward portion of the characteristics, which of course is like this. So this is the familiar static curve of the diode, and we know how this has come about. Now from this, how do we develop the photovoltaic cell model? We see that the first quadrant is involved in dissipation, and this is the dissipation mode of components, basically sinks, wherein the current flow is into the terminals as shown. The fourth quadrant is a generation quadrant. Here the voltage is still in the same direction and only the current has become negative, or current has reverse direction here, in which case the power flow also reverses direction, which means the power is flowing out of the terminals and therefore acting as a generator. So this portion of the IV characteristic is of interest to us because we would like to see how this diode can become a PV cell and also a generator. Let me drag this here, a copy of it here, and increase the size so as to make it more legible. So in this quadrant we see that the current is negative with respect to what we have represented here. If this was supposed to be the positive direction of the current flowing into the terminal, negative would be direction of the current flowing out of the terminal, and the object here, the diode in this case, plus something else, will act as a source, and the power is actually now flowing out of the terminal, because the product of these two will result in a negative value, which means negative power. So in this quadrant, fourth quadrant, this component or object is behaving as a source. But how does the current here flow in this direction? Because we all know that the diode can handle current flow only in the direction from anode to cathode. How can one make the current flow in this direction out of the terminal? Across the diode, we add a current source, IP. In such a direction, the current is flowing in this fashion as shown. Only under this condition, you will see that this current splits at this node into the diode ID as shown here and into the terminal I as indicated here. Therefore, you see that through the diode, the current is still flowing from the anode to the cathode, but at the terminal, the current is flowing out of the terminal. So if you look at this whole block as a whole, the current flows out of the terminal, voltage is still retaining the same polarity, the power is flowing out of the terminal, and therefore this whole block acts as a source. This is actually the principle of the photovoltaic cell. This current source IP is actually the photocurrent, which is dependent upon the solar radiation intensity. More the solar radiation intensity, higher is the value of the IP, larger will be this current, and larger will be the current flowing out of the terminal and therefore the power. There are a few other components and non-idealities also that will come into the model, but this basically will indicate how the photovoltaic cell is behaving as an electrical source from an electrical engineer's point of view. Let us study it just a little bit further before we develop the equations for this. IP is the photocurrent, which is directly proportional to the solar intensity, the solar power that is incident on the surface of the panel. If IP is 0, that is under dark condition, the characteristic is like this, with the bias at the x-axis line. As the light intensity increases, the photocurrent IP increases, and this whole characteristic starts coming down by an amount equivalent to the photocurrent. So increasing IP would mean the shifting of the characteristic like this. Higher the incident solar power, the more the characteristic will shift towards the fourth quadrant. So any operating point on this part of the curve would mean that the photovoltaic cell is operating in the generating mode. So normally the photovoltaic cell is considered to be a generator, and one would like to see that it is in the first quadrant. Therefore, we now redefine the current, the voltage remaining the same, but the current, the direction of the current, we will take it as positive for this axis when the current goes out of the terminal as shown here, and not like what it was defined before for the case of the simple diode. So we would not like to have this, but would like to use this as our reference now, and this we would like to bring it to the first quadrant, which would mean we have to flip the current axis, and that is done by just simple flipping of the y-axis, because the current has just flipped the direction. So this here forms the characteristic, the IV characteristic of a photo cell or photovoltaic cell. Consider the IV characteristic of a typical photovoltaic cell. Observe that for some portion of the IV characteristic, the photovoltaic cell behaves as a constant current, more or less constant current. For this portion of the characteristic, the photovoltaic cell would behave like more or less a constant voltage source. So the photovoltaic cell has this unique feature of being both a combination of a constant voltage source and a constant current source. Let us draw a line. This is the constant current line. Let us draw another line. This is the constant voltage line. The constant current line, if you take, it gives an idea of the slope of the constant current portion, and therefore it implies existence of a shunt resistance, a high value of shunt resistance across a constant current source. So we can include a non-ideality or shunt, a high value of shunt resistance across the constant current source as shown here. Likewise, the voltage line, the slope of it to the voltage portion of the characteristic would imply a series impedance in series with the terminals. So it would appear as though we have a series impedance at the terminals like this. So let us include this non-ideality also to the existing model. With minor redrawing and relocation of the components, this forms the equivalent circuit model of a photovoltaic cell. This has a symbol which looks like this. This envelope-like symbol is the symbol of a photovoltaic cell. It represents either a photovoltaic cell or a photovoltaic module. There are two terminals, the anode terminal and the cathode terminal. this is the terminal voltage and the terminal current generally flowing out of the anode terminal. So here we have the entire photovoltaic cell with the characteristic, the equivalent circuit model, and the symbol.